In this example of optimization, here's our situation. We're going to have a constraint and we're going to try to maximize or minimize something. So suppose an airplane policy states that all baggage must be box shaped with the sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square-based box with the greatest volume under these conditions? So first thing, let's draw a picture. So if we don't have a picture given to us, let's go ahead and create it. So it's a square base box. So square base. So I know that this and this match. Okay, so let's give it some dimension. But what we don't know is the height associated to it. So square base, some sort of a height to it. And we know that the sum of the length, width, and the height cannot exceed 64. So we're looking at this plus this cannot equal more than 64. So I'm just going to set it equal to 64. Technically, it's a less than 64, less than or equal to. But I feel like why would we do anything smaller? That's not going to maximize our volume. So we're going to set it equal to 64. And we are looking to maximize volume. So to maximize volume, we need some sort of a volume equation. So for our volume equation, we have length times width times height. So x squared times y. And in order for us to maximize it, we're going to do our derivative, set it equal to 0, and then figure out what critical points we have and find some maxes and mins. So problem is we're ready to do our derivative, but we have a y value in here. And so I'd like to take this constraint that we have and utilize this to sub out our y value, put it in terms of x. So if we isolate the y value, we'd subtract the 2x, so 64 minus 2x. So I can take this equation and replace the y value with 64 minus 2x. And then since we're going to do a derivative of this, let's go ahead and distribute. So I don't have to do the product rule, 64x squared minus 2x cubed. All right, so let's do the derivative. And that derivative is going to be 128x minus 6x squared. And if we go ahead and try to solve that, we can take a negative 2x out. And then that's going to leave us with a 3, sorry, this is going to be a 3x minus 64. And that was us setting it equal to 0, but go ahead and doing a step to try to solve that. So we were taking our derivative, setting it equal to 0, and we factored out a negative 2x for both pieces, just to make this a positive in the front, so we can solve it. Not that we couldn't solve it the other way, but I just like making the variable positive. So solution to this, we'll get x equals 0. And then if we solve this, we would get, we would add 64, divide by 3, so 64 thirds, which is approximately 21.3. If I throw that into a calculator, 21.3 repeating. So obviously that's not going to help us. We're not going to have a dimension of 0, but a 21 by 21 by something is going to figure out the rest of it. So let's double check though that that's going to give us a maximum and not a minimum. So critical values of 0, and then this 64 thirds. So if I take, this is our slope equation, here's our factored form of our slope equation. I'm going to plug in some values into this, and let's make sure we get a maximum out of that. We plug in a negative value, we get a positive out of this. And we plug in a negative whatever, and then subtract 4, we're going to get a negative. So that area is going to be, that section is going to have a negative slope. We plug in some value between 0 and 21, plug in a 1. So that's going to be a -2. That's going to be a 3 minus 64, which is going to still be negative, multiplied to a positive. Then we take something bigger than that, let's say 100. So that's going to be a negative. And this is going to be 300 minus 64. So that's very positive. So that's going to be negative. So we have a negative transitioning to a positive. You have a positive transitioning to a negative, and there's our maximum. So we know for sure that that 64 thirds is going to create our maximum. So let's go ahead and finish it. We've done all the math. Let's get our answer. So our answer is we want to know what the dimensions are. We know one of the values is 64 thirds, about 21.3. So then what is our other value? Do the math on it first. So to find y, we're going to go over here, and we have y equaling 64 minus 2 times, and I'm going to use 64 thirds to be as accurate as we can. 64 thirds. So that's going to get us 64. This is going to get us 128 thirds. And I need this to be thirds as well. So if I do 64 times 3, it's 192. And 192 minus 128 is 64. So 64 thirds, which is going to give us another 21.3 for the height. So, and that kind of makes some sense that the best shape that we could do, usually given some sort of a surface area kind of a constraint, is a cube. I know this isn't a surface area, but it's leading to a surface area kind of a constraint. So a cube's going to get you the biggest amount of volume with the smallest amount of surface area. Now, you can't always create a cube. It kind of very much depends on your constraints and what relationships you have going on. But a lot of times that's what it kind of ends up becoming. So our dimensions that we have for our maximum volume, our dimensions are 21.3 inches by 21.3 inches by 21.3 inches. And then our maximum volume is me taking, and I wouldn't use these values, I'd be using the 64 thirds. I would take 64 thirds cubed. And so our maximum volume is going to be, if I throw that into the calculator, 64 cubed, I would get, if I rounded to 2 decimal places, 9,709.04 cubic inches. And that was us finding a maximum volume given some sort of a dimension constraint that we have.